Today we are discussing the most fundamental topic in solid state devices, that is the semiconductor physics. And as we all know, or we have already observed from the band theory of solids, that the magnitude of the band gap of semiconductors lies between that of insulators and metals. Further, like the band gap, the resistivity of semiconductors has been found to lie in the intermediate range, also at the order of 10 to the power 13 for quartz to 10 to the power minus 8 ohm centimeter for copper and silver, and the pure silicon or germanium, which is the most pertinent semiconductor that used in the day-to-day life, lies in between, that is the 10 cube or 10 to the power minus 1 ohm centimeter. Also, over a certain range of temperature, contrary to metal conductors, the resistance of semiconducting crystals decrease with the increase of temperature. In other words, semiconducting crystals have negative temperature coefficient, that is the NTC of resistance. Broadly speaking, we can have two different types of semiconductors, that is the intrinsic semiconductors and extrinsic semiconductors. And for details of formulation of the intrinsic and extrinsic one, I will come later. But before that, few very fundamental understanding regarding the semiconducting materials, or simply uh, materials, right? Which are the new branch of physics or chemistry has been evolved nowadays, that is called the material science. So silicon is incredibly important as a material in the industry because it's a semiconductor. Of course, the name is self-explanatory, but there's more to it. The key here is the band structure, as you all know or we have discussed. Band structure refers to the bands of energy levels that form due to the sheer number of orbital states that can be occupied in molecules, right? So those that understand how electron orbitals work will point out that each energy level is discrete. But due to the sheer number of orbital configurations, a seemingly continuous distribution of energy can be seen. However, relatively large gaps still exist, known as the band gap. These are the energy state that an electron cannot occupy. The question is why that matters. The reason why it does matter is because of the Fermi level, or E suffix F. The Fermi level refers to the total chemical potential energy for a system of electrons at absolute zero. If the band lies above the Fermi level, electrons in the band can be delocalized from the atom, which means that it can carry current. The band is called a conduction band. If the band is below the Fermi level, this means that the electron is bound to an atom. The band would be a valence band. Intrinsically, a semiconductor should have its Fermi level at the midpoint of the band gap. This is true of both insulators and intrinsic semiconductors. But a semiconductor's band gap is extremely small, at the order of 1 electron volt. In fact, it's small enough that the electrons can jump the band gap uh, as soon as it gets energy from the thermal energy that will always exist in real crystals. While this property alone isn't particularly useful for digital logic, doping a semiconductor can have significant effects on the band structure. This means that the distribution of electrons in the valence band or conduction band will change. So, a simple about the semiconductor devices that we used in the laboratory for many years, that is diodes. A semiconductor device which conducts electric current run in one direction only. This is the simplest kind of semiconductor device. It has two terminals and a single PN junction. One diode can be used as a half wave rectifier or four as a full wave rectifier. The next one is the transistor. uh, because the transfer resistance like resistors, they are transistors. A three terminal semiconductor amplifying device, the fundamental component of most active electronic circuits including digital electronics. So the number one is the point contact transistor that we have usually used in the laboratory. Proof of principle device, a dead end. Then it comes the bipolar transistor, the junction transistor or the sandwich transistor, a transistor made from a sandwich of N and P type semiconductor material, either NPN or PNP. The middle section is known as the base and the other two as the collector and emitter. When used as an amplifying element, the base to emitter junction is in a forward biased or conducting condition, and the base to collector junction is reverse biased or non-conducting. Small changes in the base to emitter current, the input signal, cause either holes for PNP devices or free electrons for NPN to enter the base from the emitter. The attracting voltage of the collector causes the majority of these charges to cross into and be collected by the collector, resulting in amplification. Another kind of transistor uh, is very useful, that is the field effect transistors. Unlike bipolar junction transistors, a transistor with a region of donor material with two terminals called the source and the drain and an adjoining region of acceptor material between called the gate. The voltage between the gate and the substance controls the current flow between source and drain by depleting the donor region of its charge carriers to greater or lesser extent. Because no current except a minute leakage current flows through the gate, FETs can be used to make circuits with low power consumption. The first one is the junction field effect transistor or Jfit, where a field effect transistor in which the conducting channel lies between PN junctions in the silicon material. A PN junction acts as a diode, so it becomes conductive if the gate voltage gets reversed. And the second most important is the metal oxide semiconductor field effect transistor, or abbreviated as MOSFET. Most of today's transistors are MOSFETs that used in the amplifier or the sound systems, right? So, in case of intrinsic semiconductors, are those materials having an energy gap of the order of 1 electron volt, which is comparable to thermal energies. Hence, the conduction process in these materials is achieved as a result of thermal excitation of electrons across the energy gap. Pure chemical substances such as silicon and germanium, elements of group 4 of the periodic table, gallium arsenide, indium antimonide, silicon carbide, and lead sulfide are some examples of intrinsic semiconductors. At absolute zero, the valence band of an intrinsic semiconductor is completely filled, and the conduction band, which is separated by a distance e.g., the band gap from the valence band, is empty. For this reason, at absolute zero, an intrinsic semiconductor behaves as an insulator and has zero conductivity. Now, a simple explanation of the construction of the intrinsic semiconductors are as follows. I hope you can see my cursor. Suppose this is my conduction band. These are the bands, and these are my valence bands, right? And this is my band gap energy Eg. This is conduction band, and this is valence band. And here some electrons are seated in different energy levels or the occupied according to the material. So what happens at absolute zero, the valence band is completely filled by electrons and the conduction band is completely empty. At temperature above absolute zero, some of the electrons from the valence band right here at above absolute zero, some of has jumped to the conduction band by the application of the thermal energy. So still this is my valence band, this is my conduction band, this is the lowest unoccupied conduction band, this is the highest occupied valence band, this is EV and this is EC. So this is at absolute zero and this is for T greater than 0K. Some of the electrons from the valence band are excited to the conduction band and holes appear. These are holes, the absence of electrons in the valence band and free electrons in the conduction band that we usually conduct. As the temperature is gradually increased, the electrons of the valence band get excited. For some electrons, the thermal energy at the order of kT available at room temperature is sufficient to surmount the forbidden energy gap and move into the conduction band. The excitation of electrons from the valence band to the conduction band leaves an equal number of vacancies that are usually called holes in the valence band. Both electrons in the conduction band and holes in the valence band serve as carriers and contribute to the electrical conductivity. This is the mechanism. The another type of uh, conductors, the extrinsic conductors. Before that, another important feature of the PN junction diode uh, depending on how the distribution is changed, a semiconductor is doubled either a p-type or n-type semiconductor if the band structure is such that free electrons are more easily generated. It becomes the n-type semiconductor. If the structure is such that the electron holes are generated, it becomes a p-type semiconductor. In this case, electron holes refers to a place where an electron could exist but doesn't. Such a hole still conducts current. Look carefully at the p-type diagram once again. And because this valence band is so close to the Fermi level, electrons tend to stay in the valence band at lower orbitals. This means that there are holes where an electron could be, which makes it a charge carrier. It's also worth noting that the diagram above isn't totally accurate. as doping normally introduces more bands instead of shifting their positions, but the concept is the same. What really makes things interesting is when a p and n type junction are placed next to each other, because p-type semiconductor tend to have electron holes and n-type semiconductors tend to have an excess of electrons. There will be a diffusion of holes and electrons to try and equalize charge at the junction. Because of this diffusion process, the area around the junction becomes charged positively at the n-doped region and negatively at the p-doped region. This happens because the n-doped region is losing electrons, making the area positive, while the p-doped region is losing holes, therefore becoming negative. The result is that an electric field is generated which opposes this diffusion and eventually reaches equilibrium. The area where this process occurs is called the depletion region or depletion layer. As these ionized areas are stripped of charge carriers and therefore unable to carry current with the band structure that already exists. This PN junction is incredibly important in solid state electronics. In fact, the system we just described can be used as a diode, which is a device that only allows current to flow in a single direction. If a battery is connected with the positive terminal at the p-type semiconductor and negative on the n-type semiconductor, the holes in the p-type and the electrons in the n-type are all pushed towards the junction, which causes the depletion zone to shrink. This means that the electric field repelling the current decreases and current is allowed to flow across the junction. Okay, so this is the basic of that we understood from uh, the semiconductor physics, as you have already read in the analog electronics part of the previous semester. So now we come to the extrinsic semiconductor part. A real semiconducting crystal grown in a laboratory, no matter how pure, always contains some impurity atoms in addition to other imperfections, which create their own energy levels termed as impurity levels. These levels may occupy positions anywhere in the allowed and forbidden bands of the semiconductors. However, frequently some known impurities are introduced intentionally to impart scientific properties of to the host material. The resulting semiconducting material is known as extrinsic semiconductor, whose properties depend on the type of impurity introduced into the host material. For this purpose, normally a few parts per million of suitable impurity material is added to the melt during the growth of semiconductor crystal. For silicon and germanium, two types of impurities are used. These are from group 3 and 5 of the periodic table, that is trivalent elements such as boron and indium, and pentavalent elements such as arsenic or phosphorus that you already read in the plus 2 physics course. When intrinsic silicon is doped, it is a process of homogeneous mixing of a small quantity of known impurity into the host material with one of the group 5 elements such as arsenic. Then each arsenic atom is found to occupy an atomic site normally occupied by a silicon atom, as shown in this figure. Since the host silicon atoms are tetravalent, only 4 of the 5 valence electrons of the impurity are used in forming the covalent bond, leaving one electron weakly bound to its parent atom. These electrons can be easily excited into the conduction band by supplying an energy equal to ED, donor energy, at the order of 0.013 electron volt This electron leaves the atom and is free to move in the germanium lattice. Such an electron behaves as conduction electrons. In terms of the band theory, this process may be understood as follows. The energy levels of the fifth electron of the impurity atoms occupy positions between the valence band and the conduction band. Let me show you how it occurs. The conduction band what happens at t is equals to 0 or absolute 0, the conduction band, suppose this is the conduction band, and this is the, sorry, the pen is not working. Oh, you can see the donor level, right? These levels, what I said, the energy levels of the fifth electron of the impurity atoms occupy positions between the valence band and the conduction band, and these levels are at distance of the donor energy level at the order of 0.013 electron volt below the conduction band. At absolute zero, all these levels are occupied, but even at moderately low temperatures, most of the electrons from them get excited into the conduction band because of the small ED. The remaining positive charge or a hole is localized on the immobile arsenic atom and does not take part in the electrical conductivity. The impurities which supply electrons without simultaneously creating holes are termed as donors and the corresponding energy level as donor levels. The semiconductors doped with donor impurities are known as N-type semiconductors. Since the conduction in this case is predominantly due to electrons in the conduction band, they are called majority carriers, and the holes in the valence band becomes minority carriers. Now suppose that silicon is doped with a trivalent impurity such as indium. Again, it is found that the impurity atoms occupy sites normally occupied by germanium atoms. The indium atom is short of one electron to establish saturated bonds with all the four nearest neighbors. However, it can borrow the required electron from a germanium atom if an energy equal to AD at the order of 0.01 electron volt is supplied to the system. The transfer of an electron from the germanium atom leaves a hole in the valence band, which causes a break in one of the neighboring germanium bonds. The energy level of the impurity atoms occupy positions between the valence and the conduction band. These levels are at distance of EA at the order of 0.011 electron volt above the valence band. At absolute zero, all these levels are vacant, but at any temperature above these electrons, so between the valence and the conduction band, these levels are at a distance of EA at about 0.011 electron volt above the valence band. At the absolute zero, all these levels are vacant, but at any temperature above, these electrons from neighboring atoms can fill the vacancy and thereby leaving holes in the valence band. They establish bonds with the indium atoms and lose their ability to move in the germanium lattice and hence do not take part in the electrical conductivity. The impurities which trap electrons and add holes in the valence band without simultaneously adding conduction electrons are termed as acceptors, and the corresponding energy levels as acceptor levels. The semiconductors doped with acceptor impurities are known as p-type semiconductors. In this case, the holes are majority carriers in the valence band and the electrons in the conduction band, if any, are the minority carriers. The electronic properties of extrinsic semiconductors can be suitably described in terms of their energy band configurations plus certain intra-band energy levels introduced by the impurities, which are rather sparingly distributed throughout the host material. It is often more convenient, however, to consider the position of Fermi level when discussing the electrical and other related properties of solids. Uh, Having said the mechanism of the extrinsic semiconductors, let us consider or let us discuss the free charge concentration in semiconductors and what happens for the intrinsic semiconductors. As we know that in semiconductors, the magnitude of the energy gap, that is Eg, is very small. Therefore, some of the electrons lying on the top of the valence band gain sufficient thermal energy, which is the most usual source. Other energy sources may be electrical or radiant. Even at moderate temperatures, and get excited into the conduction band, leaving behind equal number of holes or vacancies in the valence band. In a pure semiconductor under thermal equilibrium, the number of electrons and holes are equal since they are produced as electron hole pairs, right? So these holes attract electrons in the process. One of the neighboring electrons will jump to fill the vacancy. This process will continue and is identical to the vacancy diffusion. When an electric field is applied, that is E, the electrons drift towards the positive electrode and constitute a current. Similarly, the holes move towards the negative electrode and constitute a current. However, since the electrons and holes have opposite charges, the current due to both is in the same direction. Their drift velocities under the action of an applied electric field E are V suffix electron is mu suffix electron times E, and V for hole is mu H times E, where the subscripts E and H refers to electrons and holes respectively. The proportionality factor mu is known as the mobility, the freedom of charge movement, and is a function of thermal vibration of the atoms and the crystal structure. Under equilibrium conditions, in intrinsic semiconductors, the rate of generation of electron hole pair, if we denote is by G, is a function of temperature T, depends on the nature of material and the temperature. To maintain a constant concentration of pairs, the rate of recombination, if we denote by small r, is a function of T, which depends on the properties of the material and is proportional to the concentrations of two charges, must be equal to GT. So for this consequence, our GT is equals to RT, and then this becomes some proportionality constant times Ni and Pi, the product of Ni and Pi, where Ni and Pi refer to intrinsic electron and hole densities respectively. The proportionality constant K takes into account the charge densities and properties of the semiconductor material. Now, for pair generation obviously Ni is equals to Pi, and so that our Gt will become RT, and this becomes some proportionality constant K times Ni Pi. And if Ni is equals to Pi, so simply Gt becomes Nk Ni square. And for intrinsic semiconductor, we have NiPi is equals to Ni square. Since the densities Ni and Pi are inherent property of a semiconductor at a given temperature, then the product Ni square or the square of the intrinsic charge density also has a fixed value at a given temperature and depends only on the nature of material. This result is analogous to the constant solubility product in chemistry. So in an intrinsic semiconductor such as germanium having an energy band gap of 0.75 electron volt, the intrinsic electron density at 300 K is 2.4 into 10 to the power 19 electrons per meter cube. Since germanium has 4.4 into 10 to the power 28 atoms per meter cube, it is clear that only about 5 atoms out of every 10 to the power 10 atoms of germanium will have broken valence bonds and can contribute to the intrinsic conduction as at usual ambient temperature, but increases rapidly with the temperature. In contrast, metallic copper has about 10 to the power 28 electrons per meter cube available for conduction. Since Ni and Pi strongly depends on temperature, it is necessary to limit the operating temperature of germanium devices to about 85 degrees centigrade to 100 degrees centigrade and silicon devices to 190 degrees centigrade to 200 degrees centigrade. The higher permissible temperature of silicon is because of its larger energy gap. And what happens for extrinsic semiconductor? As a matter of fact, the concentration of impurity atoms is very low, usually 1 atom per 10 to the power 6 to 10 to the power 10 host atoms, as compared to the parent semiconductor atom, and therefore impurity doping does not appreciably affect the thermal generation and recombination process. Making use of the argument that the recombination is proportional to concentrations of two charges for p-type material, this equation becomes Np times Pp is equals to Ni square. And it is to be noted that when the concentration of majority charges is increased over its intrinsic value by doping, the concentration of minority charges is found to decrease to maintain the concentration product Ni square, which is constant. Based on above considerations, the amount of reduction in the minority charges can be determined by the use of an equation expressing the overall charge neutrality of the material. That is, uh, here some, okay, even this is not written. For extrinsic, the equation is P times ND is equals to N plus NA. Now making the use of the quantity that Np is equals to Ni square, we have N is equals to Ni square divided by P, and P is equals to Ni square divided by N. And so that my earlier equation means P plus Nd is equals to N plus Na becomes P is equals to Na minus Nd plus small n, which is Na minus Nd plus Ni square divided by P. Or we get a quadratic equation of P square, that is P times Na minus Nd plus Ni square is equals to 0. Of the equation is of like quadratic equation ax square plus bx plus c is equals to 0. Therefore, the roots of the above equation are p is equals to nothing but Na minus Nd divided by 2 plus minus Na minus Nd whole thing square divided by 4 plus Ni square whole to the power half. And similarly, N becomes Nd minus Na divided by 2 plus minus Nd minus Na whole thing square divided by 4 plus Ni square whole to the power half. For an intrinsic semiconductor where Na is equals to Nd equals to 0, the equation, these two equations, if we written as A or B, we obtain N is equals to P is equals to Ni as they should be. And these are general equations for charge densities. And let us see how they change under special cases. So one condition is case 1. In this case, Nd is far greater than Ni, and my Na becomes equals to 0, right? This condition, and as well as Na is nearly equals to 0, and the hole density becomes case 1 N type, Pn is equals to minus Nd times root under 1 plus 4 Ni square divided by Nd square divided by 2. So the second term under the radical is less than unity and may be expanded as a power series. Neglecting the higher power terms, the approximate hole density can be found as Pn nearly equals to minus Nd divided by 2 plus Nd by 2 1 plus twice Ni square divided by Nd square, that is Ni square divided by Nd. Similarly, the earlier equation means this equation for N, right? This equation provides the electron density in the N-type material as Nn nearly equals to minus Nd divided by 2 plus Nd divided by 2 1 plus twice Ni square divided by Nd square, that is Nd plus Ni square divided by Nd, which is nearly equals to Nd. And similarly for the p-type semiconductors, these two approximations happens. For case 2, for p-type semiconductor, one approximation is that Na is far greater than Ni and Nd is nearly equals to 0. Then the charge densities can be found as Np is nearly equals to Ni square divided by Na, and Pp is nearly equals to Na plus Ni square divided by Na. That means equals to nearly equals to Na. So the density of majority carriers is thus approximately equal to the density of impurity atom at usual ambient temperatures. On the other hand, because of recombination process, the density of minority charges carriers remains significantly below the intrinsic Ni or Pi level. The following examples, if we consider, can be helpful in understanding in more details, right? So this is an example. The problem is that as follows: an intrinsic germanium semiconductor has a charge density of 2.4 into 10 to the power 19 charges per meter cube at 300 K, the material is made extrinsic with an indium impurity at the rate of 1 indium per 4 into 10 to the power 8 germanium atoms. If there are 4.4 into 10 to the power 28 germanium atoms per meter cube, determine the concentration of minority charge carrier and discuss the result. So what is given here? Given is my Ni, these are the given quantities, is nearly equals to 2.4 into 10 to the power 19 charges per meter cube. One impurity atom per 4 into 10 to the power 8 germanium atoms, right? Density of germanium is 4.4 into 10 to the power 28 atoms per meter cube. Now, for p-type semiconductor, we know that Nd is nearly equals to 0. Further, the density of the acceptor atom is given by Na is equals to 4.4 into 10 to the power 28 divided by 4 into 10 to the power 8, that is 1.10 into 10 to the power 20 per meter cube. And Ni square is equals to 5.76 into 10 to the power 38. Now using the earlier equation, my PP is nearly equals to Na plus Ni square divided by Na, that is 1.10 into 10 to the power 20 plus 5.76 into 10 to the power 38 divided by 1.1 into 10 to the power 20, which is 1.15 into 10 to the power 20 per meter cube, which is approximately equals to Na. And from the other equation, my NP nearly equals to Ni square by Na, which is 5.24 into 10 to the power 18 per meter. So Ni divided by Np becomes 2.4 into 10 to the power 19 divided by 5.24 into 10 to the power 18, which is nearly equals to 5. So this is the inference that Np is 1/5 of Ni. In other words, the concentration of minority charges reduces to about 1/5 of the intrinsic value. So this is a very important result. Now we quickly move on to some discussions of the mobility of charge carriers. The mobility of charge carrier is defined as the average drift velocity per unit electric field, that is mu is equals to V upon E. Therefore, this equation, the mobilities of electrons and holes in a semiconductor can be written as mu E is equals to V by E, and subsequently mu H is equals to VH by E. So in a metal where only conduction electrons flow when an electric field is applied to it, the electrical conductivity is expressed as sigma E is equals to J upon E, that is Ne V upon E, that is Ne mu E. On the other hand, in a semiconductor where both electrons and holes carry current and the mechanism of their motion is different, it is expected that their average drift velocities and hence their mobilities must also be different. So as evident from the lower picture, this one, the left one, which shows the schematically the migration of a free electron and a hole under the influence of an electric field. In both cases, electric field in the positive x direction. A free electron moves in a random path between the atoms in a direction opposite to the direction of the field, as shown in the left picture. This is the direction of the path of electron, and whereas the holes moves along the direction of the field as a result of discrete electron jumps as indicated in this figure. Here the motion is in like that way, and here this is in this way. So thus, in a semiconductor, both electrons and holes carry current. The electrical conductivity may be defined as sigma E is equals to JE divided by E, which becomes NeV divided by E, which is Ne mu E. And these two figures are the migration of a free electron and a free hole under the influence of an electric field. And this eventually becomes the mobility for hole is simply the current density over the electric field, which is NeVH divided by E, which is Ne mu H. Since the electrons and holes have opposite charges, the current due to both is in the same direction, and hence the conductivities are additive. Therefore, our total conductivity is nothing but the conductivity for electron and the addition of conductivity for holes, which is Ne mu E plus Pe mu H. If we taking common the charge of the electron, which is the same for holes, so E times N, the density times the mobility of electron, plus the density of hole, P times the mobility of holes. And there obviously the effect of temperature on mobility, the T to the power 3 by 2 law, that we'll discuss later. Now, a very important concept, what happens for the Hall effect in semiconductors. We have so far discussed the Hall effect for metals containing electrons as charge carrier. The same treatment is valid for extrinsic, whether it is p-type or n-type semiconductors, where the majority charge carrier is either electrons or holes. In the following, we shall consider the case of an intrinsic semiconductor where simultaneously both electrons and holes are present. Since their charges are different and they move in the opposite directions in an electric field, the Lorentz force, which is nothing but charge times velocity times the electric magnetic field, Q V cross B, deflects them in the same direction, that is towards the front face of the slab, this face. However, the Hall field developed by the deflection of electrons is in the opposite direction to the Hall field developed by the deflection of holes. The two charge carriers flow in the x direction, if this one the positive x direction, and the electric field Ex, according to the earlier two equations, uh, sigma E is equals to Ne mu E and sigma H is equals to Ne mu H, the current due to them is given by simply Jx is equals to Jxe plus Jxh, which is E capital Ex times N mu E plus P mu H. Along y direction, the two charges experience more than one fields, and these are Lorentz field ELE experienced by electrons and ELH by holes, and Hall field EH by both. Under the action of the fields, the current along the y direction is given by Jy is equals to Jye plus Jyh, which is Ne mu E times Ey minus Vex Bz plus Pe mu H times Ey minus Bhx Bz, where Vex is equals to minus mu Ex and Vhx is equals to mu Hex. Since the charges are not allowed to flow along the y direction, the current Jy vanishes. Therefore, setting Jy is equals to 0, in the earlier equation, substituting the value of Vex and Vhx from the equations, we obtain Ey is equals to Bzex times P mu H square minus N mu E square divided by N mu E plus P mu H. Further, the substituting the value of Ex from earlier two equations, we have Ey is equals to Jx Bz divided by E times P mu H square minus N mu E square divided by N mu E plus P mu H whole thing square. Therefore, Rh is equals to the ratio of Ey times Jx Bz, which is 1 upon E times P mu H square minus N mu E square divided by N mu E plus P mu H whole thing square. For P and N type semiconductors, these equation for the Hall coefficient reduces to Rh is equals to minus 1 upon Ne for N type and Rh is equals to minus 1 upon P for P type. So this equation, we can determine the two carrier Hall mobility as mu H is equals to sigma Rh, which is P mu H square minus N mu E square divided by N mu E plus P mu H. For an intrinsic semiconductor where N is equals to P is equals to Ni, these equations substituted as mu H is equals to mu H is equals to mu uh, for hole minus mu for electron. And since usually our mobility of electron is greater than the mobility of holes, hence mu H is negative for an intrinsic semiconductor, right? Further, from equation the equation for the Hall coefficient, it follows that in an intrinsic range, the sign of the Hall coefficient is determined by the carriers and greater mobility. Since mu E is greater than mu H, therefore, when an intrinsic p-type goes over to extrinsic range, the sign of Hall coefficient changes. Let us do it and understand it by an example. The Hall coefficient of a certain silicon specimen was found to be minus 7.35 into 10 to the power minus 5 meter cube per coulomb from 100 to 400 K. Determine the nature of the semiconductor. Further, the electrical conductivity was found to be 200 ohm inverse meter inverse. Calculate the density and mobility of charge carriers. So given here are the Hall coefficient RH, which is minus 7.35 into 10 to the power minus 5 meter cube coulomb inverse, and sigma is equals to 200 ohm inverse meter inverse. T is 300K, our unknown or want to calculate the mobility as well as the density. The negative sign of the Hall coefficient indicates that the nature of the semiconductor is n-type. Hence, the electron density can be obtained from the equation n is equals to nothing but minus 1 upon E times RH, which is happens to be 8.5 into 10 to the power 22 meter cube. And the mobility from this simple equation mu E is equals to sigma time divided by Ne, which is 200 divided by 8.5 into 10 to the power 22, which we have calculated the density times the electronic charge, which is 1.6 into 10 to the power minus 19 coulomb. And the answer is 14.7 into 10 to the power minus 3. Unit is very important. Meter square, volt inverse, second inverse. So to conclude the semiconducting properties of materials, as far as our UG syllabus is concerned, the first point for semiconductor is at an ambient temperature, the free intrinsic charge carrying concentration Ni is very small and increases rapidly with the temperature. On the other hand, the density of majority charge carrier in N-type semiconductor Nn nearly equals to Nd, and in P-type semiconductor Pp nearly equals to Na. The density of impurity donor or acceptor atoms respectively. The second one is, in general, the Fermi level lies somewhere within the forbidden band in a semiconductor. As for the effective mass of electron is equals to the effective mass for holes, the Fermi level lies exactly halfway between the valence and the conduction bands in an intrinsic semiconductor. In extrinsic P and N-type semiconductors, the Fermi level lies halfway between EC and ET and between EA and EV respectively at low temperatures. On the other hand, at high temperatures, the Fermi levels of extrinsic semiconductors coincide with that of intrinsic one. The fourth one is, since the electrons and holes have opposite charges, the current due to both is in the same direction and hence the conductivities are additive. Therefore, the total sigma of the material is the addition of sigma E plus sigma H, which is E times N mu E plus P mu H, where mu E and mu H are the mobilities of electrons and holes respectively. The mobility of a given semiconductor varies with temperature according to the relation 1 upon mu is equals to 1 upon mu L plus 1 upon mu I, which is T to the power 3 by 2 divided by A plus T to the power minus 3 by 2 divided by B, where A and B are constants for given semiconductor. At low temperatures, the ion scattering dominates, so that mu is proportional to T to the power 3 by 2. On the other hand, at high temperatures, the phonon scattering prevails, and hence mu is equal to mu proportional to T to the power minus 3 by 2. When both electrons and holes are present at charge carriers, As in a pure semiconductor, both contribute towards the Hall constant, and the resulting expression is already we have discussed, is nothing but RH is equals to 1 upon E P mu H square minus N mu E square divided by N mu E plus P mu H whole thing square. For P and N type semiconductors, this reduces to mu A RH is equals to 1 minus 1 upon NE for N type, and RH is equals to 1 upon P for P type. And the last one, and very important one, the simplest type of semiconductor junction in PN junction. A PN junction can perform various functions depending on the geometry, the bias conditions, and the doping level in each semiconductor region. Under forward bias condition, that is when the P region is made positive with respect to, yes, uh, that is a forward bias condition, that is when the P region is made positive with respect to the N region, and net current flow in the internal circuit, which is given by the very famous equation IV is equals to I0 exponential minus EV divided by KT minus 1, where V is the external applied voltage, I0 is called the dark current. On the other hand, under reverse bias condition, this I becomes minus I0, which is constant. This current is small and is independent of the voltage. So, as a reminder, or as a mnemonic, for N-type semiconductor, a semiconductor containing donor impurities, which can donate electrons to the conduction band by thermal excitation. The majority carriers are electrons. For P-type semiconductor, a semiconductor containing acceptor impurities, which can accommodate electrons that have thermally excited from the full valence band in local levels. The resulting holes in the valence band are the majority carriers. So recombination process is also there, the process by which the excess carriers produced by radiation or other means in a semiconductor crystal return to their equilibrium state when the radiation is removed. This usually occurs by sequential quantum jumps called the recombination transition. And the valence and what is the valence band? The band containing the valence electrons. In a conductor, the valence band is also called the conduction band. In a conductor, the valence band is also called the conduction band.